Hello again. How are you? I'm going to do another example of a class today. I'm going to do fractions, and I'm going to have you do, besides the polynomial you're currently doing, I'm going to have you do complex. So this kind of stuff I'm doing now might be useful when you are doing complex later. And it might not, but we'll see. All right. The game is the following. Write a C++ program to define a class fraction. Now the fraction has two fields, a numerator and a denominator. And I'm going to give it an input and an output method. And I'm going to give myself a method to add two fractions. The function that adds the two fractions is going to return a fraction. Now, I can't do it the best way I like by using the plus sign until we learn something called the friends and overloading of operators. That's coming next week, if not later this week. But right now, I'm just going to do it a fairly simple way. The real problem is when we have two fractions. How do we get the common denominator to add? You probably, I hope you remember doing fractions somewhere in, I think it was elementary school. And for example, up here, if I'm going to add 1/2 and 1/3, I have to get a common denominator of 6. And then I have to convert this to 3/6 and this to 2/6. Here on 45 and 545, I really don't want to multiply the two denominators. It'll be a very large number. I'd rather get something else. Now, what I would like to get, we would like the smallest integer that is bigger, that both denominators divide. In other words, now let's write it this way. The smallest integer that is divisible by both denominators. This is called the least common multiple, or LCM. And to get it, what I need to do is to get rid of the common parts of both of them. I need to find out what they have in common, and then I only have to use that once in getting the answer. So I'm also going to do this. I will first compute the greatest common divisor, or GCM. Now, what is that? That is the largest number. The largest number that is a divisor of both denominators. Nope, the other way around, pardon me. Yes, that's the way around. I almost had it there. So this seems like it might be difficult to do, but it turns out there's a very famous algorithm, the Euclidean algorithm does the GCM for me. GCD, I think it is, pardon me. Greatest common divisor. I knew there was something wrong there. It's not GCD. So just to show you, I'm going to go back to the here, and I'm going to put in the Euclidean algorithm, and you see it pops up right away, and it will tell you it's an efficient method. Now it comes from Euclid, and Euclid lived around 300 BC. He's one of the most famous Greek mathematicians. He actually wrote a book that was used to teach geometry up until about 1900. So it's one of the most influential books ever. And this was a question he had to figure out. What's the greatest common divisor of two numbers? Now the trick to do this, you don't need to know how anybody derived this. All I want to do is show you the algorithm, and then we'll implement it. So I'm going to take as an example, I'm going to take 225 and let's see, 7 times 35. Well, let's take 35 as the two denominators. Now the trick is that what I'm trying to do is find some way that I can write these two in an equation related to each other. And I start by taking the largest number, the larger of the two, and I put 25 there. I'm at 35. And then I ask, how many times does 35 divide 25? Now it looks to me like 7 is too much. 6, 5's are 30, 6 through 10. So 6 times that. Now that's 6 5's are 35, 18, 2, 15. So I think it's plus 10. Now what I do is shift everything over. I take the 35 and I go with the 10. And I say, it's 3 times, I'm a plus sign there, pardon me. It's 3 times 10 plus 5. And then I shift over again. And this is 2 times 5 plus 0. Now, at this point, 2 times 5, pardon me. When I get a 0, the 5 here is the GCD. Now, that you can go backwards all the way to get a relationship between the 225 and the 35 that make us equal, that bring the 5 in. But if you look at 35, it's 5 times 7. And if you look at 225, there's a 5 in it, but there certainly isn't a 7. So there's nothing else in common between them. Now, once I do that operation, then the LCM equals, take the greatest common divisor, multiply it by the denominator, the first denominator, say denominator 1, divide it by the GCD, times the second denominator, divided by the GCD. What that does is, the GCD is the greatest common divisor. I put it here and I get rid of it in the other two. And whatever's left in the other two is unique to them, and I need them if I'm going to get something that is a multiple of them. So in my case here, what I'm getting is equal 5 times 225 divided by 5 plus 35 divided by 5, which equals 45, if I'm doing my arithmetic right, and that's a times, pardon me, not a multiply. 45 times 7, and that equals 7 5, so 35, 28, 31 5. So let's see if that's right. 7 into that, 4 is 28 and 35. Yes, that's right. Now, what that means is, let's say now if we add let's see, suppose we want to add 12 225ths plus 19 35ths. Then what we do to add them is go up here and make a little more room there. We convert them to their common denominator. So in this case, the 315, we have to multiply 7 times both the, no, but I believe we don't. I've got to remember, I have a feeling I made a little mistake here. I don't know if any of you just noticed it, but I noticed it. I didn't quite get everything there. If you look at it, I got the 7, I got the 45, but what happened to the 5? There was a 5 there, then this was 45, and this was 7. So I have to multiply by this. Excuse me, I have a friend who wants attention right next to me. One of my new cats, and she's sort of insisting. So let's see what I've got here. Now I'm getting 5 5s are 25, 5 1s, that brings it to 7, and 5 3s are 15. So let's see if that's right. 5 into that is 3, 1, and 5, yeah. Okay, so what I have to do now is figure out how to do the arithmetic here. So let's see. What I'm looking at, I have to do it. I have to convert this to 1535 in 1575 in both cases. I don't feel like doing the arithmetic, so I'm going to go over and cheat. I'm going to go over here and bring up a empty file here, and I'm just going to do a little arithmetic. So let's see. I have 12. The denominator that I had here a minute ago was 225. It's now 1575. So I need 1575 divided by 225. That equals 7. I probably could have done that myself if I had thought about it, but don't worry about that. So to keep this the same fraction, I have to multiply the numerator by 7. So 7, 14, 84 divided by 1575. Now the other side, let's see, I've got in the denominator, what did I do here? 35 was the denominator. So I put 35 into 1575. Divided by 35. That's not right. Equals 1575 divided by 35. It's 45. So now I have to multiply both numerator and denominator by 45. And 45, I'm going to do it over, I'm going to cheat, equal 45 times 19. 855 divided by 1575. And that equals, I might be able to do this arithmetic, 93, that's 8, that's 8 and 85, and then 9, and then divided by 1575. Now that might not be the smallest. It might be that there's a common factor in those, but I'll worry about that when we do the program. That looks very complicated, and I know it is. And I'm not even expecting that you would understand all that. The mathematicians among you should have some idea of it. GCD is a very, very common algorithm used in lots of things. And this is not too hard to program. In fact, I've already programmed it. It's right down here. And there's the two functions to do it. What I did for the GCD is I first decided which one was the largest. Well, first, if the two are the same, it's obvious that that's the common denominator, the least common multiple. Otherwise, I want to check. If den 1 is smaller, then the left side should be den 2, and the right side should be den 1 to begin. Otherwise, it's the reversed order. So all I'm doing is getting it so that I have the larger one of the two on the right, on the left, when I begin my work here. Then I do what I did there. I do the arithmetic. So now, while the right side does not equal 0, so actually I went one step further than I did up there, I compute the new left side to be the right side. I'm just passing it over. And then the right side equals the left side mod the right side. And then the left side equals what I had computed. I'm in the same problem that I had when we did complex multiplication. I needed to save the left side so I could use it down here. Now what that really means is I went one step further in my calculations here. What I really did was I went 5 equals 1 times 0. And that way it was easier for me to see what it was. Now, once I got the GCD, it was easy to get the least common multiple. It's here somewhere. There it is. I made great the GCD, and then, as I've set up above, great appears once in the LCM. I get rid of it in both of the others, and whatever is left by those divisions is the unique things in denominator 1 and denominator 2. So those two were like functions I needed to make things work. Now let's look at the program and we'll be able to run it. So I wish to name a new class. The class is going to be fraction. As usual, fraction needs to have a generic constructor. So if I just want fraction, I don't want to read anything in, I don't want to start it off anywhere. I just use the name fraction. You notice that I need an empty function here, and just a nothing program to implement fraction. Then here, since this was a very short program, I put it in here. I didn't bother writing it later as I will for the other functions. But this just says, if you want to put in the numerator and denominator, I've given you a way to do it. Then there are only two fields in this, the numerator and the denominator. I didn't protect them. Maybe I should have, but I didn't. And then I have void input, void output. Notice there's no addition. That's because add is not a member of these at this point. Add is a function that's going to use them. I can't attach it to one of them easily. It would mean I'd have to change one of them, and I wanted to do it this way, so to leave the original two alone. So here's what I did. There's the two functions. Now here's my output. You notice I just did a simple output with the division sign between them. I thought that would work nicely. For my input, I asked the user to input the numerator and the denominator. I could have read in a fraction with the slash, read it as a string, and then did some arithmetic with it, some tearing it apart to get the two numbers. I decided for this case I wouldn't, but I might when I expand this later. Now the add. I want a fraction as the output. Some of you, maybe not all of you, may notice something. Fraction has two parts, a numerator and a denominator. And no function can return more than one thing. However, a fraction isn't two things. It's one. It's an item of type fraction is a variable, one variable. So even though it has two parts, I can return it from a function. That's another good reason to use classes. It makes it reasonable to write it as it's going to return a fraction to me, not pieces of a fraction. So in here, I do the arithmetic. I compute the common denominator using LCM. Then I compute the numerator of A num and the numerator of B. I didn't have to compute, and the denominator is just the common denominator. The numerator is the sum of those two numerators. And then I did a little more arithmetic. I checked to see if the two sums, numerator and the denominator, might have something in them. If they don't, the GCD will come in 1. Otherwise, I'll divide it out, so I'll get down the lowest terms. In my main line, I did a very simple routine. I just read to, add it, output it, put a plus sign between the two numbers, output it, put an equal sign, and output it the answer. This isn't the perfect way to do it, but we don't have the tools yet to write it perhaps the way I would like to. That's coming. But it does make it easier. And when I was writing the main program, I didn't have to think of any of the details. This would be the kind of thing where somebody, maybe me, would write the LCD, the GCD and the LCM routines for you, so that you wouldn't have to know about them, but you just have them there. And you'll notice in this, I didn't use them. They're hidden in the details, which is a good idea. So let's run it, see what happens. Okay. Well, maybe we should run it with what we have from here. So, what to now? Pardon me. I'm moving things all around that I shouldn't. It was this I wanted to move. And I need to know what the two numbers were up here that I use as my example. All right, let's try these two. So bring this up again. I want 12. It's just 12 225ths plus 19 35ths. The answer is 313 over 525. It turns out there was a common item between the two. And so it was able to get rid of it. In fact, I could tell right here it was 5. It's pretty obvious that there was a 5 between them. I probably should have noticed that myself. I think that was it. Yeah. No, it wasn't 5, it was 3. This is divisible by 3, so it's 313. This is divisible by 3, and you get 525. So there's an example of it. There's another one in the what I am sending you as the notes here. I have another example of a run of it. Down here I ran 2 cases, just to give you 2 examples to see how it works. And that's an example of using a class. Now, the point I made, and I want to repeat, is that if I'm just a user of the class, I don't have to know the details. I don't have to know how to add the 2 fractions. I don't have to know a single item about common denominators, or how to figure out if they're in lowest order or anything like that. Those are hidden in the implementation of the addition. That's if I'm a user of the class. If I'm an implementer of the class, then I better know how to do these things, or find out how to do these things from somewhere so I can do them. So that's it for now. What I'm going to do is give you a problem involving the complex numbers. Then my next video is going to begin talking about overloads. overloads are very, very important. They're part of the whole theory of classes. The point of an overload is that instead of writing up here a dot input, I'd rather write cin chevrons A and cin chevrons B. And instead of that sum equals add A plus A comma B, I'd rather write sum equal A plus B. But what that means is I need to give a new meaning to the plus sign. I need to give a new meaning to the two chevrons that mean input. So that's called overloading them, giving them another meaning besides the ones they have. By the way, the plus sign is already overloaded. If I have two integers, A and B, plus does integer addition. If I have two reals, A and B, plus does a double addition. And if I have two strings, or a string and a character, it does append, as we were doing in the homework involving the Caesar code type items. So plus is already pretty nicely overloaded. We're going to overload it a few more times. That's it for now. In case I don't make my video before the weekend, I want to wish all of you a happy Easter or a happy Passover. I hope you will have a chance to enjoy time with your families if you can get home, and we'll keep going. So long now.